representing the second element, which is capacitor. So we will be examining as we did it for the inductor. We are going to repeat step by step what we have done for inductor. We are going to repeat it for the capacitor. What is ideal capacitor? Just click here, see inside. Conductors separated by dielectric material makes a capacitor. So you've got two conductors and separated with a dielectric inside. That makes a capacitor. So it says separated because of that dielectric material, separated electric charge causes electric field. So moving current causes the electromagnetic field, but this separated charge causes electric field. So capacitor has got electric field. Energy stored by the initial condition of this voltage of the capacitor is the initial condition, is the energy storage element. It is a linear element, it is a passive element. So why it is so? Let's see it. Commercial capacitor. So the capacitor parameter that is shown by a word letter C. The value range in electronics is nanofarad, microfarad, and millifarad. Nano is 10 to the power minus 6. Nano is 10 to the power minus 9. Mu is 10 to the power minus 6. M is 10 to the power minus 3. So when this goes up, this size goes up. So the biggest one, millifarad ones, is in the range of centimeter, the physical range of it. It says common capacitors are in the range of micro and nanofarad ranges. So these are the common capacitors that we see. Micro, nano, milli, not that common. Oh, it's still common. Okay. So this is how we see this element in market. And how we are going to represent this element mathematically in circuit theory comes to this one. So since it is a separated plates here, the charges has been separated. There are two parallel. So we show the capacitor like that. And these are the voltage and current references of the capacitor. So voltage and current references shown here is fitting to the passive sign convention. Under these references chosen according to passive sign convention, the definition relation of this element is this. The only difference between the inductor and capacitor is that in inductor we have taken derivative of the inductor current. In here we are taking the voltage derivative. We are taking the derivative of the voltage of a capacitor, get the current of the capacitor. So this is the definition relation. Definition relation has got the derivative in it. Because of this derivative, the equations that we are going to solve at the end for analyzing circuits which includes L and C elements in it, they are going to be differential equations rather than linear equations. That is the reason. So what is that? This C here is called the parameter of this element. And C is related to the physical and the chemical properties of this element. Depends on that. Since it is a quantity related to the physics and chemistry, then this C value should be positive and real value. See, it won't be negative. Okay. So if you know the voltage, you can find the current of this element. If it is the opposite, if you know the current of this element, then you're going to take the integral of it, multiply it 1 over C, get the voltage of this element. At the same time, through the mathematics, you're going to get a term here. It is called initial condition. So this initial condition is related to voltage. In the inductor case, it was the current. So inductor's current has got an initial value, capacitor voltage has got the initial value. So if you multiply this current and voltages, you get the power. If you get the integral of this power, you're going to get the energy. At the end, the calculation of the energy gives you that formula. That formula tells me for any t value, that energy becomes positive, because C, I know the C is positive real number. Then Vc, wherever negative it is, since I'm going to get the square of it, it's going to be positive. So this equation here is always positive for every t. That means this element is a passive element. That is the definition relation of a passive element. What about linearity? We are saying it is a linear also. This is a linear element. Why is that? Because the derivative operation and also the integral operations are all linear operations. How I am calling these operations are linear? Because we already proved that, for example, summation of the two functions derivative is equal each function's derivative's summation. You could use this for the integral as well. So summation of the two functions integral is equal each function's integral's summation. So that is the definition of linearity in mathematics. Since the definition relation of these elements are linear relations, then these elements are called linear elements as well. By just looking at these definition relations, there are so many things that we could say. The another thing that we could say is the voltage instantaneous change cannot happen for the capacitors. Why is that? Because if there is an instantaneous change or discontinuity in that VCT function, that means derivative of it is undefined, because uncertainty, discontinuity point, you cannot find the slope of the tangent. That's derivative. You cannot find that. In mathematically, you cannot find it. In physically, that means there won't be any discontinuity in the voltage of the capacitor. What about the current? You don't say anything like that for the current of this element. The reason is that because of the integral. If there is a discontinuity in that current here, you could find out the area underneath that function. Why is that? You're going to find the area before the discontinuity point, an area. After the discontinuity point, another area. When you add them up, you can get the area underneath the whole curve. That's why there won't be any problem. There won't be any problem in mathematics, means in practice there could be a discontinuity for the inductor current. No problem there. Another way of looking at this definition relation is easy. So you can say that this element could be used finding the derivative of a function. So whichever function derivative you are looking for applies as a voltage source to a capacitor and measure the current. That current would be the derivative of the voltage. So by definition you can easily say that. You could say the opposite as well. If you apply a function IC as an inductor capacitor current, then if you measure the voltage, that means you can find the integral of this function. So in old days, in analog computers, these elements have been used in order to find the solution of the differential equations. One more thing that we could say just by looking at the definition relation of capacitor is that if a DC source is applied at a capacitor, DC source means VCT is equal to a constant. Derivative of a constant gives you 0. That means capacitor current is 0. So if you apply a DC source to a capacitor, So the current is going to be 0. That means the open circuit. So capacitor becomes open circuit if there is a DC source on it. So we examined here, by just looking at the definition relation, there are, we could say, some of the properties of a capacitor, so we just said that. And let's come, if we apply different sources, what happens? So in here, there is a strange independent voltage source applied to a capacitor, of which capacitance is C equal 0.5 farad. There is, we can divide this function in 3 areas, less than 0, t is negative, then it is, the value is 0, this area, and this function here is for t between 0 and 1, t equals 0 and 1. After t1, the function here that we observe here is this function. So that's the voltage change. If you get the derivative of this and multiply it with c, you get the current. So since this is, this slope has got, there is a slope here, the derivative gives you that slope. That slope of this line, so it's going to be a constant, and derivative of this is giving to you this. So just by looking here, I can say that the voltage is always positive, but the current becomes positive, and this time interval is going to be negative. So multiplication of those two is going to give you a positive area and a negative area, and multiplication is the power. So once again, this power negative, so it's giving the power, you might say, but this power is not this element power. Why is that? Because this power already been taken from this independent source. So this element is not an active element, but this and an active element. In this time interval, the energy or the power of this element are transferred to that capacitor in this time interval, in here, and then the stored energy, which is absorbed from this independent source, is going to be released. That means giving back to the source. Therefore, we are going to say this is, so on the other hand, if this area, that's negative area, is less than this positive area, that means the energy is always positive. So you could see it in here, because these functions, underneath of this function, you're going to see an area, this summation of those two is always positive here. So it becomes negative if this negative area is bigger than the positive area. It becomes negative. When it becomes negative, then it is an active element rather than passive element. So in this case, it is a positive element. So we could always say that. Why is that? Whatever source you apply here, this property of this element do not change because of this relation. We already proved mathematically whatever source you apply, because of this formula here, the energy of this element is always positive for all t values. Therefore, it is a passive element. We have just show you one example for this. The another example here, if we apply a pulse, but this pulse is an independent current source, so you're going to get the integral of it. So you're going to get that red one. This is the voltage. That's the current. That's the voltage integral. And then multiplication of those give you that green one. And the integral of it gives you the energy. So the energy is always possible. You could mathematically, you can easily say that. So after t equal to 1, since the voltage is 0, multiplication is going to be 0, the integral of it is going to be 0, that's why the energy after t equal to 1, then it is 0. Okay. So the last step is serial connected capacitors and the parallel connected capacitor. When the capacitors are connected in serial, so you could do proof your own by using the Kirchhoff voltage law equations in here. If you replace these elements capacitance inverses, find the inverse of these equivalent capacitor. We are saying this voltage and current here, whatever it is here, is going to be the same as here. That's why we call it equivalent capacitor. What about the initial conditions? So if we consider the Kirchhoff voltage law equations, these are the initial conditions of these voltages. So if you replace these elements with just one element between those two terminals, the voltage, initial voltage value that you're going to observe is going to be the summation of these initial voltages. So that is also true for the initial voltages. So when it is parallel, you could just add up all these capacitor values to find the equivalent capacitor. So you're going to use the Kirchhoff current law equations in order to prove that relation. So you could do it your own, easy to do. So that's going to be the end of this video related with the capacitor. So let's finish in.